This is ACT Math Additional Concept Vectors. ACT Math Additional Concept Vectors. Vectors are not extremely common on the test, but they have been showing up with more frequency on some of the more recent tests. So if you are going for a massively good score, you will probably want to know a little bit about vectors. The good news is that the vectors questions that have popped up on the test have been relatively mild in difficulty as long as you know some basics about vectors. That is what we will cover here. So first of all, what is a vector? We're going to go ahead. Oh, by the way, you may want to have graph paper for this particular section. Lined notebook paper will do fine, but graph paper might make things a little bit easier, especially to make what you are writing on your paper look pretty much exactly like what I am writing on my paper, which is what you should be aiming for. Quantities that have both a magnitude is just a fancy way of saying size, magnitude and a direction. And we're going to put in parentheses here as opposed to scalar quantities, which have only a magnitude. In mathematics classes, the vast majority of numbers that you encounter are scalars. They only have a magnitude. When it comes to vector quantities, however, and some examples of vector quantities, for those of you who have taken physics, these will be very familiar to you. That's not what I wanted to write, not vectors. I wanted to write velocity, force, acceleration. These are quantities that when we express them, we don't only talk about their size or their magnitude, we talk about their direction. For instance, again, for those of you who have taken physics, you might be familiar with a force diagram where you draw different forces acting on a certain object, and you might draw one force acting in this upward direction with a certain size arrow, and then another force acting in this downward direction. So forces can be indicated by arrows. We're going to talk more about this in a moment, where the size of the arrow indicates the size or magnitude of the force, and the direction of the arrow indicates, of course, the force's direction. You might have forces that act in the rightward direction or easterly direction. You might have a large force acting in the westerly or leftward direction. So these types of quantities we express with both a magnitude and a direction as opposed to simply a magnitude. Very frequently, you will see vectors expressed in the following way. Let's go ahead and write down often expressed as a directed line segment. And that's really just a fancy way of saying an arrow whose length indicates the vector's magnitude. So we may see a vector. I'm going to do this. Let's do this. Let's go from this little corner of the grid up till here. So we're going over 1, 2, 3 and up 1, 2. So we're going to make a vector there, and we'll call that vector A. And what we say when we express a vector as these directed line segments is that let me get rid of that stuff there. This end of the arrow of the directed line segment is the tail. This end is the head. And the size of that arrow indicates the vector's magnitude. Now, keep in mind, some students will ask, what is the difference between an arrow like this and a ray? And the difference is that, number one, one of them is a vector and one of them is a ray. And number two, vectors are finite. This arrow at the end of this vector does not indicate that the vector continues in that direction infinitely, as would a ray. It simply indicates, that arrow indicates the direction of the vector. Doesn't indicate anything about the vector continuing. It just indicates that the vector heads in this sort of northeasterly direction. But the size of the vector is finite. The vector goes from here to here, and that would indicate its magnitude. For instance, if I were to draw another vector, I'm going to go straight across the page here. I'm going to draw another vector that has exactly the same magnitude as A. Let's call this vector B. But let's put the tail, let's put the head, the arrow down here. So the tail is up here, the head is here. So vector B has the same magnitude as A, but it has the opposite direction. Vector B heads in this southwesterly direction. Now what I'm going to do is let's do this. We're going to go over about 1.5 of these grids. We'll go up to there. So this vector C appears to have the same direction as vector A, looks sort of parallel to vector A, but it's about half the size of A. A would go all the way up to there. Vector C is half the size of A, so vector C has the same direction as A, but about half the magnitude, half the size. We might get a completely horizontal vector. Let's do maybe something like this. Is a big magnitude vector right here. That vector is completely horizontal. We can call that vector D. And again, you can see vector D has, of all the vectors we've drawn, it has the largest magnitude, the largest size. And then maybe we do, I don't know, here's a little sort of 1 unit vector pointed downwards. And then over here, let's draw one final vector. We'll call this vector F. There's vector F. And we should be able to see that vector F is absolutely identical to vector A. Vector A and vector F, they both head in the same direction, and they both have the same magnitude. They both have that 1, 2, 3, 1, 2, 3 horizontal components and 2 vertical components, or a sort of getting from the tail to the head, we go 3 to the right and 2 up. Same thing with A, 3 to the right and 2 up. So because vectors are defined only by their magnitude and their direction, vector A and vector F are identical to each other, even though I have written vector A over here on the left and vector F over here on the right. It does not matter that they are in different places on the page. All that matters is they have the same direction and the same magnitude. So that might be something you want to note over here. Note vectors have no fixed location. It's not like if I move vector A over here to where F is that I get a different vector. I get exactly the same vector if I simply translate or shift a vector. If I were to move vector F, you don't have to draw this. I'm just going to draw it and then erase it. But if I were to move vector F down here, that's yet another vector that is identical to vector F and vector A. So that is one of the ways that we notate vectors as a directed line segment. By the way, on a vector question, you may occasionally get something like this, where they label one end of the vector as R and one end as S, and they might even notate that as vector RS. Again, this is not ray notation. In the context of vectors, this would mean vector RS. They also may notate, one other way they may notate vectors is they may notate with a non-italicized bolded letter. So for instance, vector A here might look, I'll try to bold this as best as I can. So they might say vector A, they might call vector A this non-italicized bolded A right here. So there's multiple ways that they can notate vectors. Now, when we talk about these directed line segments, these arrows, we often will plot these arrows on the XY coordinate plane or on the rectangular plane. So let's jot that down. Often we'll plot these directed line segments, I'll just call them arrows, on XY plane. So for instance, let's draw this here. We'll draw a vertical axis, our y-axis, and we will draw a horizontal axis, our x-axis. And I am going to pretty randomly place the tail of a vector at the point 1, 0. And I am going to place the head of that vector 3 to the right and 4 down. So let's say we've got a vector that heads in that direction and has that magnitude. So this directed line segment, this arrow, is now plotted on the XY coordinate plane. We can see the tail of the vector is at the point 1, 0. The head of the vector 3 to the right and 4 down would be at 4, -4. Again, it is important to understand that that vector, I just randomly and haphazardly plotted that vector where I did. I could have started the tail of that vector over here at -1, 2, 3, 4, 1. So that's -4, 1. The vector would go again 3 units to the right and 4 units down. So where would that take me? It would take me to here. So this vector over here, I'm going to make that into an arrow. So again, 3 to the right, 4 down. The head of this vector would be at -1, -3. These two vectors, even though they are plotted on at different points, their tails and their heads are at different points on the XY plane, it does not matter. They have the same size. They have the same direction. Those are identical vectors. Again, I can take this vector, I can translate it over here, I can translate it over here, I can translate it down here. As long as that vector stays the same length, the same magnitude, and the same direction, it's the same vector. Doesn't matter where it is on the XY plane. Now, in terms of magnitude, let's go ahead and write this down. Let's write determine magnitude of vector. And here's what I'll do. I'm going to call this vector A. And again, I'll put it in that sort of bolded A. The magnitude of vector A might be notated like this. You might see sort of this absolute value sign and the letter A, the name of the vector inside the absolute value sign. That will indicate that you are talking about the magnitude of the vector. In other words, the length of that directed segment. You can determine the magnitude of the vector using the vector's horizontal and vertical components. I'll tell you what I mean by that in one moment. In the Pythagorean theorem. So, a moment ago, I said that to get from the tail of this vector to the head of the vector, what we do, and I'm going to color code this. You don't have to color code it if you don't have multi-colored pens or multiple colored pens. If you do, you might want to color code this just so it's a little bit easier to see everything. So what I said was that to get from the tail to the head, what we do is we go 3 horizontal units to the right, and then we go 4 horizontal units down. So technically that's down 4 units, but I'm just going to put 4 for now because we're dealing with distances, and distances don't have signs don't have negatives and positives. So we're going 3 to the right, 4 down. So if we were doing Pythagorean theorem here, what we would do is I'm going to say 3 squared plus 4 squared equals the magnitude of a squared, which for now I'll just call c squared because that's what Pythagorean theorem would normally look like. We do 9 plus 16 equals c squared. We do 25 equals c squared. We square root both sides. I'm going to flip so that the c is on the left. We get c equals 5. Now, of course, if you are familiar with your Pythagorean triples, you would have known that this is a 3, 4, 5. Anyway, that 5 right there, that 5 is the magnitude of this vector. The length of that segment, of that directed segment, is 5, and that 5 is the magnitude. That is how we can find the magnitude of a vector. If we want to find the direction of the vector, so directions / angles can be found using inverse trig functions. Now, some of you may not be familiar with inverse trig functions, or maybe with trig functions at all, and that's fine if you're not. Just try to follow what I'm doing here, but this might seem a little bit unfamiliar to you. So suppose that you were trying to find the angle in here that vector A is making with the horizontal. So that x-axis there, that's the horizontal axis. And suppose you were being asked what this angle is in here. Well, we know all 3 sides of this triangle, so we could technically use any of our sine, cosine, or tangent functions. I'm going to go ahead and use tangent. I'm going to call that angle theta. I would know that tangent of theta has to equal the opposite side 4, over the adjacent side 3. That's what tangent equals. That comes from opposite over adjacent. Tangent equals opposite over adjacent. Now, to get that theta isolated out of there, what I do is I just inverse tan both sides. I'm going to write it like this just to save some room. So I'm going to inverse tangent that whole equation, and the theta gets freed up, and what I have on the right is inverse tangent of 4 over 3, and I go right into my calculator, and I make sure I'm going to go in degree mode. I am in degree mode. Quit out of there, and what I do is I do second function tangent or inverse tangent, and I'm going to enter this as a fraction. So I'm going to do 4 divided by 3. Oops, let me get that parentheses out of there. It actually doesn't really matter, but let me close the parentheses over here. Even though I don't have to, I will. And what I get is 53 degrees. So theta equals 53 degrees. That means that that angle that this vector makes with the horizontal is 53 degrees. It also tells me that this angle in here that the vector makes with the vertical is 90 minus 53, whatever that is, 37 degrees, I guess. So that is how you can find directions and angles when we graph a vector on the xy coordinate plane. What we now have to talk about is now have to talk about some alternate notation, some other notations that we might see pop up. So let's say alternate notations. And first we will talk about, so by this point we've already talked about several different notations. We've talked about the directed line segments up here. We've talked about the fact that they can sort of be notated like rays. They can be notated with these bolded non-italicized letters as opposed to variables that come in italics. So a couple of other notations we have. Component / rectangular notation. And that simply looks like this. It looks a little bit like an ordered pair, except with these little alligators on the left and right, or these almost greater than, less than signs on the left and right instead of parentheses. So what component notation is, I'll actually give you an example here. So let's do negative 3 comma 2. That negative 3 would be the horizontal component. That 2 would be the vertical component. And when I say component, basically all I mean is how we would proceed, how we would travel from the tail to the head. This notation tells us that if we start at the tail, we'd have to go 3 left. That's the negative 3. And then we would have to go 2 up. That's the 2. So if we look at this on the xy coordinate plane like we were doing before, and again, I will just, I will put the tail of a vector at the origin. It's an easy place to put it. What this component notation tells us is that we want to go 3 to the left. From the tail, we go 3 to the left, and then we go 2 up. And it is at that point where that green arrow ends that our head of our negative 3 comma 2 vector will be. It is this red vector that has components negative 3, 2, a horizontal component of 3 to the left, a vertical component of 2 up. If we had a component notation, so as another example, let's do a component notation of 0 comma negative 1. What that would indicate, and again, I'll just randomly put the tail of a vector, I don't know, here. 0, negative 1 would mean that we go 0 to the left or right. Okay, that's the horizontal component. So we're not going to the left or right at all because that component is 0. And we are going 1 down, 1 unit down. The vertical component is negative 1 to get to the head. So the vector with these components would look like this vector here, 1 unit in the downward direction. The other notation, speaking of a 1 unit vector, the other notation that we might see is we might see ij notation. And I don't want to spend a lot of time on this because this is quite simple and pretty much identical to component notation in that ij notation really just has a lot to do with how far to the right, left, how far to, up and down we go. So ij notation, we're going to write down I and j are the horizontal and vertical unit vectors. And by unit vectors, we're just talking about a vector with magnitude 1. That's what it means to talk about a unit vector. So for instance, a vector with these components, negative 3 comma 2, could also be expressed in ij notation as this, negative 3i plus 2j. What that means is that our vector has 3 I or horizontal unit vectors. And if we look back up here, we can see that there is 1, 2, 3 unit vectors sort of stacked head to tail. And the reason that they are going to the left is because of that negative. Okay, if that 3 were positive, these guys would be going to the right. We would have 1, 2, 3 to the right, but since this is a negative 3 in front of that I, what we are doing is we are taking the horizontal unit vector, a horizontal vector of magnitude 1, so that vector right there, and we are multiplying it by 3, but we are flipping the direction on each of those. So that's where that horizontal component comes from. And then that 2j, again, j is the vertical unit vector. So what I am doing is I am going up 2 vertical unit vectors. 1 there, 1 there. Okay, so that is 1j, and that is another j. This is 1 negative I, this is another negative I, this is another negative I. So that is ij notation. By the way, this vector and component notation up here, or rectangular notation up here, in ij notation, let me get back to red here. ij notation, that would be, I'm going to sort of write this like this. It would be 0i. We don't have any horizontal unit vectors. And then we have 1, we can write negative 1j, although we don't really need to write that negative 1. We can just write negative j. So this vector right here that simply goes down 1 vertical unit could be notated in ij notation as a negative j vector. That is ij notation. Now we do need to talk about vector calculations. Vector calculations. And basically what we're talking about here is vector arithmetic. We're going to be multiplying some things and adding some things and subtracting some things. We are going to start with scalar multiplication. Scalar multiplication. And I'm going to use component or rectangular form here to notate this. Bring that back down. Let's do this. We're going to do n and then x comma y. This n right here, that's the scalar that I'm multiplying by. And all I do when I have a scalar, remember a scalar is just a number. That's all a scalar is. That n might be a 2 or a 3. All I do with scalar multiplication in component form is I simply distribute that n to both the horizontal and the vertical component, the x and the y. So what I would end up with is a vector that has these components. That is not what I meant to do. So I would have a vector that has those components, horizontal component of nx, and again, that's just that scalar times whatever that x component was originally, and again, the scalar times whatever the y component was originally. So and oh, by the way, you can see in that word scalar, we have, without the e, of course, we have the word scale. That's what a scalar is doing. It is scaling our vector. It is basically elongating or even compressing our vector. I will show you what that looks like in a moment. Let's just do a quick example. Let's say we have a scalar, or just again a number, an integer of 2. That number doesn't have to be an integer. It could be 1/2. It could be an irrational number if you wanted it to be. Let's do this. So again, all we would do is we would distribute that 2 to each of these components. So we would end up with a -6 horizontal component, and we would end up with a 4 vertical component. So multiplying this scalar by a vector with these components would give us a vector with these components. Similarly, in ij notation, we'll just use the same example. This vector in component or rectangular notation would have -3i plus 2j. That's the ij notation. And same thing, we would simply take that 2 scalar and we would multiply it by both our I and j parts of ij notation, and we would get -6i plus 4j, which again mirrors what we have over here in component notation. Now I do want you to know what this would look like on the xy coordinate plane so that you can get a sense of all the different ways that we can think about what multiplying by a scalar does. I would draw something like this. Actually, I apologize. I'm going to move this over here a little bit. Oops, that arrow didn't quite get over there, did it? So let me get rid of that. There we go. So now what I'm going to do is I'm going to draw this vector here. So remember that vector is 3 to the left. That's the -3. and 2 up. And again, I'm just putting the tail of the vector at the origin simply because that's an easy place to start. So I'm starting from a tail here. I'm going to the left 3 and up 2. Again, a -3 horizontal component, that's that guy right there, and a +2 vertical component, that's that guy right there. So what is happening is I am getting ahead of the vector. I'm not getting ahead of the vector. I'm getting my vector's head at this point here, which is really the point -3, 2. There's the origin, 0, 0. So this vector is ending at -3, 2. Now, when I multiply by a scalar, I can think of this in several ways. One is, as I said a moment ago, scalar means I'm scaling. So it basically means that I'm simply multiplying that original vector by 2. Here's the original vector, and now I just scale the vector by 2 so that I am now ending up at this point here, which should be -6, 4. Now, if I look at the components of this vector rather than looking at the vector itself, I should be able to see that if I scale each of the components, I will go -3 and then another -3. So again, I'm just multiplying that -3 by 2, and now look what I'm getting. I'm getting a horizontal component of -6, so that's 6 to the left from the origin, and I am getting a vertical component. If I scale that vertical component by 2, I come up here to whatever that y value is, but remember I can take those two vectors, those two green vectors stacked on top of each other, and I can translate them over here, which is what I'm doing. And now I can see I have a 4-unit vertical vector there over on the left, and indeed I'm going 6 to the left, 4 up, which also brings me to the point -6, 4. I even could write that horizontal component, that first -3 there, and that second -3 there. So I go over 3 up 2, over 3 up 2. Either way, doesn't matter how I envision this or how I conceive of this or what order I do this in, either way, I had a vector that started at the origin and ended at -3, 2, and when I scaled that vector by 2, both the original vector's components and the original vector scaled by 2. Everything scaled by 2. In terms of magnitude, I do want to point out that the magnitude of that original vector by Pythagorean theorem would be, let me get back to red here. By Pythagorean theorem, that original vector would be c squared equals 3 squared plus 2 squared. Again, that's just sort of a and b, so a squared, b squared. That means c squared would equal 9 plus 4. That means c squared would equal 13. That means c itself would equal root 13, just square root both sides there. So the original magnitude here was root 13. It stands to reason that if I scale that vector by a factor of 2, meaning I just pile another vector right at the head of my original vector, I have another root 13, which means that this total distance, this total magnitude, should be 2 root 13. Well, let's see if everything comes together here by doing Pythagorean theorem on the components of the big resulting vector, the one that goes from 0, 0 all the way to -6, 4. The components are the 6 and the 4. So over here, what I'm going to do is I'm going to do Pythagorean theorem again with the 6 and the 4. So 6 squared plus 4 squared. We can see that those are just double these two numbers, 6 squared, 4 squared. C squared equals, that's going to be 36 plus 16. That's going to be 52. I'm doing this in my head and I shouldn't be, but I'm doing it anyway. And then when I square root both sides, what I get is I get C equals 52 can be broken down into 4 times 13. That's root 4 times root 13, and indeed that root 4 becomes 2 root 13. So again, just showing you various ways that we can think about this, various sort of orders of steps that we can go through to arrive at the same conclusion, even ways that we might be able to check our work by knowing the different ways that we can arrive at these answers. So again, that original vector here to here, the scaled vector from the origin all the way up here, original magnitude was root 13, new magnitude is 2 root 13. so on and so forth. Now we are going to do vector addition. Now vector addition, some students do find vector addition a little bit challenging, a little bit tough to understand, but we'll take it slow. It shouldn't be too difficult. So we're going to do vector addition, and again I'm going to show you how to deal with this in multiple ways. With let's do ij and component notation at once, because these are the simplest to deal with. So ij and component notation. So what we do with ij and component notation is this: we simply add like parts. That's all we do, is we add like parts. What the heck do I mean by that? I mean this. Let's say we are adding a vector, I don't know, let's call this vector A. So this is vector A, and we are adding that to vector B, which will have components, let's do -3, -5. How about that? Well, all we do is we add the like parts, meaning we add the horizontal or x parts of each of these to each other. So we end up with -4 for the addition of those two. And we add the y parts, the vertical parts, so the the 5 and the -5, that would be 0. So when we add these two vectors, A and B, we get a resulting vector of -4, 0. The resulting vector will go -4 to the left and nothing up or down. In terms of the arrow graph notation, arrow/graph notation, let's take a look at what this would look like. What we use is we use the tail to head method. And once we connect the tail to the head, what we do is we connect, I'll show you what this means in a moment, we connect the open or loose ends, the open ends. So I'm going to draw a fairly large XY coordinate plane here. Let's try that. We might have to adjust this in a moment. I will start by putting the vector A, and again, just doing this randomly, I'm going to put vector A over here. I don't know, I'm going to put its tail there. So to get from the tail to the head, remember for vector A, I go 1 to the left and 5 up. That's what those components are. They're basically a little map. So 1, 2, 3, 4. Ooh, I'm going all the way up there. Okay, so let's see here, we'll do vector A, there's vector A. Okay, so that is vector A. And then vector B, where do I want to put vector B? I don't know. Let's put vector B here. So that is, so vector A, sorry, this is -3, -1. And we are going up to -4, 4, I believe, I hope. Vector B, we will again randomly put its tail at 1, 2, 3, 4, 5, 1, 2, 3. So that is 5, 3. And vector B, the components tell us we need to go 3 to the left. 1, 2, 3. And we need to go 5 down. 1, 2, 3, 4, 5. So those are the components of vector B, and what I'm going to do is I'm going to connect the tail of that blue vector to the head of that red vector, and that is my vector B with components -3, -5. Where is that point? That point is 2, -2. Great. So now I've got my two vectors plotted on the XY plane, and again they are plotted wherever the heck I want them to be plotted, simply because it doesn't matter where we plot them. I could have put A over here, I could have put B over here, as long as I'm getting the right components, 3 left, 5 down, 1 left, 5 up, it doesn't matter where I plot these. So here's what the tail to head method says. The tail to head method says that I need to translate or shift one of these vectors. This is how I add these vectors. I need to translate or shift one of these vectors so that the tail is at the head of the other vector. So what I'm going to do is I'm going to translate that tail, which is right now at -3, -1, and I'm going to move it all the way over here and down here. In other words, I'm going to put that tail right at the point 2, -2, and you can see that that's simply a translation of 5 to the left and 1 down. That's not all that significant, but if you've done translations with function graphs, you understand that functions can move, left, right, up, and down. That's all I'm doing with that vector. So same thing as before. Now what I'm going to do is I'm going to go 1 left. Okay, again, I'm just using my components here. 1 left, and I'm going to go 5 up. 1, 2, 3, 4, 5. So now vector A is here. And you can see that I now have the two vectors that I am adding, A and B, tail to head. I have the tail of vector A at the head of vector B. I'm going to write down A there. And now I am ready to add. And the way that I add is, and this is where color coding would come in really handy. But again, if you don't have color coding, just do your best. What I do is I connect the open ends to form a new vector. So my new vector is going to go from the open tail to the open head. That tail of vector B to that head of vector A. That vector right there, that is the sum of vector A and vector B. And now what I do to express that vector, we can talk about its magnitude in a moment. That shouldn't be too hard to find considering this is a horizontal vector, but we're going to talk about the components of that vector. That blue vector, we can see this in a couple of ways. Visually, we should be able to see, so I'll just write down visually. We should be able to see that when we add vector A to vector B, we get a vector that results in those components. We're going 4 to the left, 1, 2, 3, 4, so the horizontal component is -4, and we are not going up or down at all, which means that our vertical component is 0. So that's visually how we can just see what this vector is, what its components are, I should say. And if we want to look at the components of the original vectors of vector A and vector B, the two vectors that we were adding to get that resulting vector, well, look, the blue, the dark blue, I'm going to get that sort of out from under the light blue one. The dark blue vector, horizontal vector for B was -3 and for A was -1. So we're going 3 to the left and then another 1 to the left. We could even put that other 1 here. So same thing, we're going 4 to the left, right? -3 and then -1 is a total of 4. And then look at the green vectors. We go down 5 and then we go right back up 5. Okay, so again, adding the components of the two vectors, the green components, the vertical components, we're going down 5 and up 5. Well, that's a net movement of 0. We haven't moved up or down at all overall. And again, you can see that in the addition of the components. We are going left 3 and then left 1. So we get the -4, we get the -4, we get the 4 to the left, and we are going 5 up and then 5 down, or 5 down and then 5 up, 5 down, 5 up, 5 up, 5 down. Those two components, those two vertical components cancel each other out. And again, we can see in the light blue vector that is the sum of A and B, that we are not moving up or down at all. So that is how we do vector addition using the XY plane. When it comes to vector subtraction, maybe we should add subtraction there. We need to know that subtracting vectors, so we'll use this same example. Let's say instead of A plus B, we were going to do A minus B. So this would be -1, 5 minus -3, -5. So again, that's vector A minus vector B. There's a couple ways to think about this, but probably the easiest in terms of component or rectangular notation is just to understand that subtracting a vector is the same as adding -1 times, so that's a scalar right there, -1 times the second vector. So basically this would become -1 comma 5, that's still a, and then we would be adding to that 3 comma 5. Now it is, oops, that's not supposed to be a parentheses. It is important to note that 3, 5 is actually vector b, but in the opposite direction. You'll remember at an earlier point in the video, I had said that flipping the vector, let's actually scroll up there so we can see that. I had said that vectors a and b up here had the same magnitude but opposite direction. Well, this vector b would just be equal to -1 times vector a. What that negative does is it simply flips the direction of the original vector. In other words, the negative just puts the tail where the head was and the head where the tail was. So in this example at the bottom, what we would be doing is we would be adding that -1, 5a vector to no longer the -3, -5, but a +3, 5. So the b vector would simply be, the head would be up here. And now what we would do is we would have to take that a vector, and we would have to put it up here. So you would get, let's actually do this. I think I'm going to make each of these 2. So so this will be 2 this time, 2, 4, 6. So the b vector is now 3, 5. So I'm going to put its tail there, 3, and then 2, 4, 5. So the b vector would be there. So again, that's b. And at the tail of that, at the head of that, I'm going to put the a vector. And remember that is -1, 5. So we're just going 1 to the left. Remember that's 3 there. We're going 1 to the left and 5 up. So this is 2, 4, 6, 8, 10. We are at 5 there. So we need to go 5 up, which means we're going to go up to the 10. So the a vector would be there. And now the resultant vector would be this guy here. Again, we're just connecting the open ends, the tail of the original b vector to the head of the a vector, the tail of the b to the head of the a. And what we should be able to see, and we can inspect this visually first. It looks like we're going for that light blue vector. We're going to the right and 10 up. So it looks like the light blue vector would be 2, 10. It looks like that's what the components would be. But let's look at the components of the b vector, or the negative b vector, I should say. We're going 3 to the right, and then we are going 5 up. That just comes from the vector's components. And then for the a vector, we're going 1 to the left, and we are going 5 up. So we go up a total of 5 and 5, which is 10. There's that vertical component of 10. And we are going to the right 3 and then back 1. We're going to the right 3 and then left 1. Well, there's that 2. That's the net movement. 3 to the right, 1 back is a net movement of 2 to the right. So indeed, both from just visually inspecting this light blue vector and from analyzing the components of the 2 vectors that we were adding or subtracting, we can see that that light blue resulting vector has components 2, 10. And by the way, again, in terms of magnitude of that blue vector, we would just do Pythagorean theorem. So the magnitude of the blue vector, again, we'll do c squared equals 2 squared plus 10 squared. So that is 4 plus 100. So c would equal the square root of 104. Not sure if that breaks down, but I don't really care. It probably does, because I think 4 goes into that. But anyway, that is how we subtract. I do also want to point out that we could have even put the a vector down here. We could do the a vector, you know, instead of up here, we could put it down here. Same thing is going to happen. We're going to be going up 5 and up 5, so we'll have a vertical component 10. We'll be going we'd be going over 1 and then back to the right 3. We'd be going left 1 and then to the right 3, so we'd still get that 2 component. It doesn't matter which head to tail we choose. We can put either head to either tail. It doesn't matter. And by the way, we can confirm the outcome, that 210 outcome over here with our component notation. Remember, we just add that -1 to that 3, we get a 2. We add that 5 to that 5, we get a 10. And easy peasy, we're done. You may ask why the hell we would do this question in this way over here as opposed to just adding the components, and the answer is it's fine. You can add the components. There's nothing wrong with doing that. I will tell you that depending upon the way the question is set up on the actual test, you may get a question on which it is actually easier or even necessary to add the vectors using the arrow notation or using the XY coordinate plane. That is pretty much it for vectors. So again, we've got to know what a vector is. We've got to know all the different notations, the arrows, the components, the rectangular, the IJ. We've got to know a little bit about vector calculations, scaling a vector, adding vectors, subtracting vectors. As long as we have a relatively general sense of how to do this stuff, we should be okay. In a separate video, I will work through a couple of the vectors questions that have shown up on the test.